Happy New Year. Welcome to the new semester. We're really excited to kick off Tux for 2019. I'm very excited to be here introducing Steve Feiner for our Sanders Series Invited Lecture. So any successful scholar will know that we need to stand on the shoulder of giants to be successful in our careers. And while I don't suggest anyone tries to climb up Steve's back and physically stand on his shoulders, he is truly one of the pioneers and visionaries in our field, specifically virtual reality, augmented reality, computer graphics, and 3D user interfaces. Steve is a professor of computer science at Columbia University, where he directs the computer graphics and user interfaces lab. So for over 25 years, they've been making contributions to VR, AR, and wearable computing, including creating the first outdoor mobile AR system using a see-through head-worn display and GPS. This was back in 1996, called the Turing Machine, T-O-U-R, so fun play on words. And of course, many, many years before things like the Google Glass, which we are seeing in widespread commercially available usage today. So his work has really had an immense impact on the field, and I will do my best to summarize some of those ways. But academically, he's published hundreds of papers, and his work has been cited over 40,000 times. And he's also a co-author on the seminal textbook, Computer Graphics, Principles and Practice. As an academic supervisor, he's graduated many PhD students who now are leaders in the field themselves, such as Blair McIntyre, professor at Georgia Tech, who is one of the leaders in augmented reality research, and Jorge Benko, who leads the research efforts now at Facebook Reality Labs. So Steve's contributions have been recognized with some of the most prestigious awards in the field. He's a fellow of the ACM, a fellow of IEEE, a member of the Chi Academy, a recipient of the ACM SIG Chi 2018 Lifetime Research Award, the IEEE ISMAR 2017 Career Impact Award, the IEEE VGTC 2014 Virtual Reality Career Award. In 2010, he won the ACM WIST Lasting Impact Award for his paper, Windows on the World, 2D's Windows for 3D Augmented Reality, which is, again, a pioneering piece of work for our field. This was published in 1993. He's also won Best Paper Awards at WIST, Chi, VRST, ISMAR, and 3D UI. Now, I've told you about all these incredible accomplishments, but to me, what's amazing about Steve is the efforts he's made to help build our research communities. He's served as general chair or program chair for dozens of ACM and IEEE conferences. But more importantly, at least for me, he's incredibly welcoming new members to the community. So personally speaking, as someone who did my PhD research in 3D user interfaces, obviously a lot of my work was built upon or inspired by Steve Feiner. And to be honest, the first time I met with him and worked with him as a junior member, as a part of a program committee meeting, I was a little bit intimidated to work with him. He was incredibly open and friendly, made discussions very easy, and in general treats all of his colleagues, regardless of their seniority level, as equals, which I think is extremely important. And I think the students who've had the pleasure of working with Steve would agree the amount of emphasis he places on the next generation of students. So please help me in warmly welcoming Steve Feiner.
Thank you very much, Toby. I'll try to see if I can live up to that great introduction. It's a pleasure to be here. As the title of my talk says, I'll be talking about user interfaces for collaborative AR and VR. My lab has been doing for a number of years now user interfaces in general for AR and VR in a variety of different domains. Navigation, you're seeing at the left-hand side of the screen over there. Let's see if I can even point with a laser pointer. There we go. Some work that we did in outdoor AR with a big bulky backpack. That's actually Jorge Benko when he was still a PhD student working with me, wearing one of the somewhat lighter weight generations of a ridiculously bulky backpack. games and entertainment of various sorts, like this little marble maze game that you see me demonstrating in the inset in the center, and task assistance of various sorts, with people being assisted both by systems. Get a little closer to the mic, okay? Is that better? If I'm not loud enough, please let me know, okay? By doing some kind of a gestural thing with your hands. So task assistance where the computer is assisting you, task assistance where another human being is assisting you, whether they are co-located or remote. So the charge that I see my lab investigating is basically effective user interfaces. And there's a question that we ask that underlies much, or maybe even all of what we do, which is how can, at least for AR and VR, how can AR and VR help people accomplish whatever goals they have, whether it's to work or to play, more effectively, whether they're working individually or together. And the thing I'm going to concentrate on in this talk is the together part, okay? Collaborative user interfaces, with human beings working with each other, and in fact, as you will see towards the end of the talk, not just people working with each other, but different kinds of display and interaction technologies working with each other. So one question that we want to ask is, why now? So why is this a really good time to concentrate on doing things collaboratively? Well, an easy answer is to look at all the devices that we can play with, things like, for example, the Rift, which are priced at the level at which a 12 or 13-year-old kid who really wants to play with stuff like this, probably, if their parents were well off enough, got a system this past holiday season, maybe even the holiday season before that. So we've got Rift, we've got things like Windows mixed reality headsets like this Samsung HMD Odyssey. We have things like the Vive Pro, a little bit more expensive than your typical 12 or 13-year-old would want to be able to spend, would be able to spend. They would want to be able to spend that. But now we're also moving into things that, because the Vive Pro has a pair of cameras at the front, lets you do AR as well as VR, in this case video mixed with the stereo pair of camera images. And of course we've got things like the HoloLens and the Leap Motion, Magic Leap rather, different Leap, which are all devices on the right side there that are optical see-through head-on displays. Again, a bit more expensive than your typical 12 or 13-year-old would have, but well within the range of what researchers who hadn't really been thinking about AR and VR would be able to get. So all this stuff is now available, and so suddenly we can do things without having to have double of a very, very large budget to be able to go and do them with. So let me give you a little bit of context just to try to help you really appreciate why this is a very special place to be. And so what we want to do is to look back a half century ago. And normally in our field, you don't say things like a half century ago. Until very recently, you couldn't. There wasn't a half century ago in real interactive computer graphics and HCI. But if we go back in time, literally 1 month ago, 50 years ago and plus 1 month, December 1968 was the Fall Joint Computer Conference, and that's the one at which Doug Engelbart and crew did what is often known as the mother of all demos, right? A way of referring to it that Andy Van Dam is responsible for having coined. Now this demo, which involved video conferencing and text processing on computers, this really blew people's minds when they got to see folks interacting across space, literally many miles away on the two ends, through analog video actually being sent back and forth. And I'm assuming everybody here knows about this, because if you haven't, you can find online the videos. They're really fascinating to watch. But to really get some little bit of context, I want to mention one thing. This is not only about video conferencing, it was about actually using computers to edit text of the sort that regular, normal, non-scientific programming human beings would want to read. And you can see off on the left over there some of the text from the screen. It was an old vector display that was aiming basically a beam of electrons at phosphor, lighting them up, and yet you're seeing black and white characters there because they then took a regular normal black and white television camera, aimed it at that vector display, reversed the video, so suddenly you're getting black on white, and they were therefore able to use much less expensive displays for multiple people to have those displays. But one interesting thing is, if you look at all the text there, it's all uppercase, right? Now, people see those little horizontal bars over some of the characters. You know what those are? Those are the characters that are really supposed to be uppercase. The vector generator built into this thing, which had special electronics to be able to generate little curvy things like characters, not making them out of little straight vectors, only did uppercase. And so that's how they showed you that the C in credits, for example, had to have an uppercase C. So if you think about that mindset to go into a world in which computers only did stuff in uppercase and say, hey, let's use it to actually edit the kind of text documents that people back then were doing on typewriters, pretty damned amazing. Now, I'm really talking about VR and AR, and interestingly, at that very same conference, although not done as a demo, was this paper. Ivan Sutherland's first paper on a 3D head-mounted display, now 50 years in the past, with a full optical see-through stereoscopic VR system with two different kinds of 6 degrees of freedom head tracking. But unlike the stuff that was being done by Engelbart, which is very collaborative and people working together, this stuff, the technology was much more expensive, much more finicky, much more special case. They had one head-worn display. Okay? So this was not collaborative. And literally an entire room worth of stuff needed to go and make it work. So the great thing now is, of course, 50 years later, plus 1 month, right? We now have all of those really neat things very affordably, and in terms of the quality, tracking quality, display quality, much, much better. So let's go right now back to the present, back to the various kinds of devices that I was mentioning. And now what I want to do is to talk about some of the work that my lab has done in collaborative AR and VR. So one of the task domains I mentioned before, which I'll talk a little bit about right now, is remote task assistance. So how can we help people helping each other when they're not in the same place? And there is a very classic model being used in many, many different fields, in which you have a local person who actually is where the action is, where the thing that needs to be fixed or maintained or operated, and they are there. And sometimes they don't necessarily have the skills, especially to deal with things that are not really expected. And then you have a remote, in industry they're called SME, or subject matter expert, who's going to be advising them. And sometimes the remote advice doesn't work all that well. You have to fly that expert in to go and work with the person who is where the action is happening. And they might spend a whole lot more time on the plane to get there and literally solve the problem in 5 minutes. And it's something that nowadays, if you can do it over phone, that's okay. If you can do it with FaceTime, that's okay. But if it really involves really being boots on the ground and interacting with physical components in a very 3D kind of way, that's hard to do with current technology. And so one of the things that my lab is interested in is how can we try to get some of that sense of being there by not actually being physically there. And there's two kinds of things that we're interested in having these remote subject matter experts do. One of them is helping to get our technician into place, getting them the where that they need to be relative to the stuff that they're working with. And the other is, once they're where they need to be, helping them actually perform the task, okay? Showing them what it is they need to do from the vantage point that is the correct one. So that's kind of the combination of where and how. So what I want to do is to talk a little bit about some of the stuff that we've done in trying to use VR and AR to deal with letting a remote person help with the where and the how. So the first thing I'll mention is some work that we did back around 5 or 6 years ago. This is the getting in place part. And what you're seeing here, and I'll show you some videos shortly, but I want to set it up for you, basically is what our remote SME sees in a task that involves getting our technician to be in the right place relative to a turboprop engine aircraft engine that I happen to have in my lab. I have a real, genuine Rolls-Royce Dart 510 engine in my lab. And what you're looking at here is a small scale model that is a full-sized hand of our expert being tracked with depth camera-based tracking. And you can see the size of the model relative to it. There is a tracked Lazy Susan that you can see circular profile at the bottom, letting you turn the engine around easily instead of having to move around it. And we're now seeing basically our view of what our SME is seeing. And then off on the left, you're seeing a little sphere with a piece of pyramid sticking out of it, and that is just the tracked position and orientation of the head of the local technician so that our SME knows where they are. The SME's hand is pointing to this funny looking little red shape, and that represents a way of representing where we would like to have the technician go. Okay, so this is showing or letting the SME pick one of a set of positions that have been, and orientations that have been decided to be good ones for the technician to be in. Now, I'll say just a still, this is what our technician sees. You're seeing the actual real engine at the left. This is done in video, see-through AR. I'll show you some video shortly. And we have this thing that looks kind of like a splayed picture frame kind of window. And in this particular approach, which is one of the first ones that we did, the idea is we want to get our technician to look through that window. And if they're looking through the window, the idea is they're in the right place and looking in the right direction. So let me show you what that looks like when it's actually running. And so here we see an external view of our remote expert. They're spinning around that little Lazy Susan. There is our model of the engine. And what they're going to do is to move their hand in place over there and point to one of these little places that represents where we want them to go. Here is our technician wearing a video see-through head-worn display. And they're going to look through that picture frame window. This is one eye of what they're seeing. They're going to walk over to where it is, and they look through it. And then when they look through it, our SME can now proceed to go and point to what it is that they want them to see. In this case, we've extended Pinocchio nose like the finger with a nice long pointer to make it easier for them to point instead of having to really reach in and point at stuff. So this is an approach that we were playing with back in 2013. And one of the interesting issues about this is that notion of what you do when you tell a person to look through the window. And there's some people who, if you say the window's over here and they see it over there, they'll walk right up to it and they'll stick their head through it and they'll look through it. Okay? Now there are other people, because it looks a little bit maybe like a frame in a painting, who often go to art museums. They know if they get that close to the picture frame that the guard is going to, notice what's going on and run over there and tell them to keep back, keep your distance, right? And so different people approach that picture frame in different ways. Some people are very respectful, stand back. Some people get closer. And we're really trying to figure out, is there a way that we could tell people graphically much more precisely or fuzzily where we want them to be, okay? Now, there's one approach that we've used and other people have used where you literally give people essentially something that looks like the classic computer graphics frustum. There'll be like an eye point, stick your eye at the eye point, look around the central line of the frustum. That's great for bore sighting tasks, like looking through a microscope, where you're very limited as to where your eye can be. But for things like what I'm doing right now, giving a talk, if I had a lavalier microphone, I could be walking around in the front. They're all good positions, facing roughly the audience. Here I'm constrained by this mic. I'm trying to stay close enough to it. Maybe I'm not always succeeding. But if I turned around like this, and I spent a lot of time looking like that, that's wrong. This is good, this is good. These are all pretty good positions. None of them are necessarily better, although maybe with the microphone, the really close ones are. But we were trying to get some sense of being able to come up with something that would let us capture the fuzziness or lack thereof of position and also of orientation. So what we came up with is something we call a ParaFrustum. And what you're seeing over here is a particular visualization of it. This thing looks a little bit like an automobile airbag in the process of getting deployed into the face of the person standing there wearing the head-worn display. And what's going on basically is that this is a representation that tries to capture some of the fuzziness of position and orientation. And so what you're seeing here basically is the airbag thing is what we call the head volume. And when you see this thing, you're instructed that you need to get your head inside of this. And you're seeing this from your standpoint. This is the third-person view, obviously. I'll show you some video of a first-person view very shortly. But I want to just set this up. You need to get your head inside the head volume. And there'll be some graphical things going on that will help you make sure you do this, because there's no actual force that you're going to feel. If you go all the way through it and out the other side, you won't really feel anything. So it all has to be done, in our case, it's all done visually. And we also have this tail volume you're seeing there. And let me explain how the tail volume helps you in orientation. So I'm going to show you a couple of stills from a video, which will, I hope, get this across. We're going to read these in row major order, starting at the upper left. And so you're seeing a view, again, one eye of our technician, who sees, in this case, a somewhat smaller volume that they need to get their head into. This is more constraining of position. Both eyes need to be inside of that little volume. Here in the middle top row, we're getting a lot closer to it. And so it's obviously looking bigger. We're kind of lining ourselves up. On the top right, we've gotten our head inside of it, and you're seeing a set of these little ribs. The ribs actually are wrapping what in this particular implementation are two ellipsoids. Our head and tail volumes are ellipsoidal. They're wrapped in the convex hull by those, the ribs are representing part of the wrapper that isn't actually touching those two ellipsoids. And once your head is inside, then the ribs disappear if the tail volume, which I'm not sure you can see it, but there is, if it were darker here, you'd be able to better see. There is very faintly over here, easier to see in the headboard display, the thin red outline of that tail volume. If that's within both eyes' view, then we're okay. The ribs disappear. That's a good view. And if you can move around your head inside, you'll be positionally right. And the way we do the is it really good is by making sure that that tail volume is properly adjusted relative to the two frusta. So the first thing I'm going to show you is in the lower left-hand corner, we've gotten our head inside of that head volume. Now we've exited. We've gone too far, and when you go too far, that thin red line starts glowing a kind of angry red. The ribs come back that's saying, no, 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 get further back. And in fact, for the sake of showing all the visual things that it shows you when you're doing things wrong, in the middle one at the bottom, you're seeing a little sort of white border at the top and the right, because to approximate making sure that you can actually see enough of the tail volume, we basically have a rule of thumb that says the tail volume, if it's protruding from that combination of the left and right eye frusta on only one side of left and right, you need to move around until it gets fully inside or protrudes on both sides, okay? Because it might actually really be too big and there's no way to actually encompass it. Sometimes that will be the case. So it's going to glow that angry white, okay, if it's only cutting out on one side of left and right or one side of top and bottom. In this case, we're a little bit too high up on the top, a little bit too far over on the right. And then at the lower right-hand corner, everything is okay. Probably can't see it, but that red outline is fully visible, and the ribs have disappeared, and that's actually one of a set of good views from this standpoint of being the right position for the head and the right orientation. Clearly, the position and the orientation and the sizes of those ellipsoids control what's going on, and they're designed to make it very easy for you visually to be able to have the sense of doing it right, and if you're doing it wrong, what you need to do to go and fix it. So having given you that little preview, let me show you this actually running. So here we have looking through one eye, we're getting our head into it, it's still yellow, and now when the head is inside, the ribs go away, everything is great, but we're gonna stick our head out the other side. It's getting really red, that means get back, but no, we're gonna go and cut it on the right and the top and the left and maybe not the bottom, and then we'll pull back. And now this is good, all these views we're looking around right now, these are all good ones, and then we pull back and go out again. So the idea is to make it very easy for you to be able to get, to know when your head is in the right position and orientation, when there is a range of possible positions and a range of possible orientations. So that's some work on trying to get you in the right place. Now let's look at trying to get you to actually do the right thing. So I'm going to show you some images and some video from a demo that we did at SIGGRAPH, I want to say last year, but this is actually 2017. So a month ago, it was last year. So now this is a year and a half ago. And so here we're looking at how we actually get a person to perform the task. And in this work, we have a local technician who's working in augmented reality. We have a remote subject matter expert who's working in virtual reality. And the reason that we did this combination is we want the local technician to really have a lot of situational awareness, to really see at full resolution, optical see-through display in this case, the real world with additional overlay graphics. And our remote SME, well, everything is being done virtually because how do you get to be a SME, a subject matter expert? Well, it's like the old joke about how do you get to Carnegie Hall, practice, practice, practice. You practice a lot for many, many years. It takes time. It can take not just years, but decades. And at a certain point, maybe you are the most qualified person in your entire company to know how to fix things. And you've been at the company for 30 odd years or so, and you're thinking, you know what? I want to retire. And if you tell that to the company, maybe if they really love you a lot, they'll say, hey, how about a raise? And you might literally say, double my salary? No thanks. And you walk out the door, and out the door walks 35 years worth of experience. So the idea is, what if you could capture that by having people, when they retire, be willing to make the deal that, yes, I'm gonna, whenever I want to, I'll give you a little bit of advance notice. I work from home. I'm not going to have to come to the company. I don't have to have a disgusting engine sitting around in the family rec room. Everything is done virtually with the head-worn display. I don't have, the company will give you one. Your kids can play with it. Your grandkids can play with it, when you're not using it. At a certain point, you reach the point at which people will say, yeah, sure, why not? And the idea, on the other hand, of being retired and still being useful and still being able to hang around with people that you actually enjoyed hanging around with, but not 9 to 5, 5 days a week, and do it only when you want to, I think can be really appealing to people. So that's why we're making our remote SME do stuff in VR. So what's happening over here? This is the task domain that we used for our demo. And so our remote SME is going to show our local technician how to install some gears in the right location. So we're tracking everything in 6 degrees of freedom using classical optical mocap technology. This is a natural point OptiTrack system. We have a aluminum chassis that is tracked in 6 degrees of freedom, a set of gears on some axles. Off on the right, you're seeing a pair of gears that have sort of an ungainly way, these little retroreflective markers attached to them, so the system knows their position and their orientation, as well as the position and orientation of the head of the technician and of the board itself. So you can pick the board up, move it relative to the gears. Everything is being tracked. There's CAD for absolutely everything over here. And what's going to happen then is we've got our technician. They're performing their task in AR. Everything, as I said, is tracked in 3D. They're looking at the world through a stereoscopic optical see-through head-worn display, a Meta 2 in this case. And here is our SME. They are interacting with a live virtual copy of the technician's task environment. Sometimes in industry, people talk about so-called digital twins, in which you're monitoring everything about some potentially complicated physical asset. Maybe electronic as well, all the things that are happening with it, and then you can basically do things with it, maybe diagnose problems with it remotely. And so in this case, our SME is going to demonstrate a task to the tech in VR. They're going to grab hold of stuff, in this case using Oculus controllers. They can reach out, they can manipulate things that are in this live virtual copy of the technician's task environment. So one interesting issue here is virtual proxy for every item in the task environment. All these things are being controlled by the technician who actually picks these things up and moves them around. But as a remote SME, I want to be able to say, hey, you need to pick this up and move it in place like this. Now, if I grab hold of that thing, which is being tracked physically in the technician's environment, there's going to be a disconnect because now the SME is moving it over here, but it's sitting physically, because there's no robotics doing anything. It's sitting physically in the same place, and that just is not going to jibe. And so what we do is When our SME reaches out to grab something, they actually automatically create what we call virtual replica of it. They get to control it. It looks a little bit different. It's semi-transparent over here. They grab hold of it, and they can actually show what's going on, okay? And they can show the technician what to do by moving this virtual copy that is seen in the technician's field of view into the right location, orientation, and of course they're also talking as well, because voice over IP is, other people worry about how to do that really well. So, let's see what the technician's view looks like. I'm going to show you a view through that head-worn display. This is being shot through a little RGB camera that's actually in it, but it gives you a very good idea of what the technician is actually seeing. And so you're going to see basically the SME demonstrating stuff, and the technician is then going to follow by following the demonstration. And so here we're seeing the Semicontrolled replica. There's a little rubber band line showing which one of those gears needs to be moved if you forgot where that replica is emanating from. And our SME then picks up the other one, moves it into place, puts it on the axle, and then our technician puts it in place as well. This is a very simple task. We promised the SIGGRAPH when they accepted this thing that we would take no more than 5 minutes per person, and that has to include getting a head-worn display on. Many people, but not all, had worn rifts. Pretty much no one had actually worn a Meta 2. And so just getting the technology on, showing people what to do, was a substantial amount of time. And so the task had to be really easy. To make things more interesting, normally I said this is a subject matter expert. Well, we let SIGGRAPH attendees be both. And while they weren't bad at playing the person who didn't know what they were doing, they certainly didn't know what to tell the person what to do. And so our system actually has built into it assistance for the SME, who isn't really a SME, as well as assistance for the expert, as well as assistance for the technologist. And in this case, those rubber band lines are being used on both ends. They're being used for the technician. They're also being used for the SME, so the SME can confidently know which thing to go and do stuff with, what axle to put it on, and then when the technician does the right thing, things will highlight in a way that lets the SME say, hey, that was the right thing to do. So they don't really need to be a SME. So let's see what they are dealing with. Here's the SME's view. We're looking at all the CAD for the parts, well, properly positioned in orientation, oriented. They're holding a pair of controllers. Each controller is created equal. You can do stuff with your left hand or right hand or whatever is the most natural for you. And now we'll see basically what the SME is doing. And so here they're going to go reach out. We let them grab anyone they wanted to. They grab hold of it. And there's a rubber band line for them, showing them which axle to put it on. And one thing to notice is when it gets close enough, that's the technician doing it, they're going to really have to put it on. It's a little square hole and a square cross-section peg. But for the SME, they know how to put it on. The technician knows how to put the gear on as well. They just don't know which gear and where. And so to make life easier for the SME, rather than making the SME actually have to line the gear up so that the square virtual hole fits over the square virtual axis without any force feedback, when it gets close enough, it just spins into place. Because that's not the problem. Our technician knows how to put gears on. In fact, that actually was a physical problem at SIGGRAPH. There's a surprising number of people who don't know how to put a square hole gear on top of a square cross-section peg, even when you tell them. So interesting range of abilities, which required a little bit of extra assistance. So a lot of these things that I'm going to talk about have user studies associated with them. My lab evaluates stuff. We do controlled studies. And in the interest of time, I've left out all the slides talking about the studies and how they were constructed and how they were evaluated. And I'm happy to talk about those things with you later. So now I'm going to move to another task domain for collaboration. And to do that, I'm going to show you a picture. How many people know what this is? What's this a picture of? Any guesses? Yes?
New York.
New York. Okay, that's not a bad guess. Everyone guess New York? Okay. Well, it's not really New York. If you look at this kind of carefully, it looks a little funny, right? it's a little, the colors aren't really quite right, okay? And the reason that they aren't, this is not actually Manhattan, which you're seeing, but it is in fact a scale model of New York. It, at the time at which it was built in the early 60s for the 1964 World Fair, and to this day, is the world's largest scale model of a real city. It's nearly 100 feet on a side, currently in the Queens Museum, which for the World's Fair was the New York City Pavilion. It was put together under the aegis of Robert Moses, the so-called master builder of New York. And the idea was, in part, to make for an awesome experience for people attending the fair and attending the pavilion. Did I mention that every single building in the entire 5 boroughs is actually represented in that model? Every building. Some better than others. The Empire State Building looks pretty good. The bridges look pretty good. The kind of buildings that normal people live in that aren't big apartment buildings didn't look all that good. But they were there, every single building. Because the idea was, when the fair was over, remember, this guy is in charge of planning for New York City. He now has this big, beautiful scale model where you could walk around the outside of, I would want to say with a laser pointer, but lasers had just been invented around then, and the word didn't even exist until the 70s. So with a flashlight, you could imagine people saying, what if we put the bridge over there, right? And looking at all this in 3D. Now, nowadays, when you do this with a computer, but computers didn't do stuff back then. Remember, this is before Engelbart, this is before Sutherland, right? You know, and this is a lot of buildings, you know, taxing even now to put up all those buildings with the full resolution that you'd like. And so with this idea, this, if you think about it, I talked about digital twins before, this is kind of a physical twin of the city, and a very nice sized one. It actually had little planes coming in to land on little wires at the airports and blinking lights, and the buildings were painted with fluorescent paint so you could actually put the black lights on and have them look like they were lit up inside. And some buildings really had real lights inside. They put a lot of effort into this, a lot of money, to be able to do that kind of urban planning. So the idea is, with all those things that I mentioned, rifts and Vives and HoloLenses and stuff, the idea of being able to do this virtually suddenly becomes really, really feasible. Feasible even if you're a 12 or 13-year-old kid, and collaboratively if you're as the 12 or 13-year-old kid, visit your friend who also has a system, go into their basement, and now you have a collaborative VR system, right? Better than anything that a researcher would have had not too many years ago, and you got it basically for the holidays. So what you're looking at here is a virtual model of New York. We're using a model from a company called World, but there's a number of other companies that also have similar models of urban infrastructure. However, we're doing something that wasn't being done in that physical model, and that's that we're going out to a variety of databases. In New York, we went out to New York City Open Data, which has lots and lots of databases. They're all open, as New York City Open Data would imply. And what you're looking at here are a set of records for 311 calls. That's the number that you call in New York if there's a non-emergency. You really shouldn't tell the police about it, but it's a pain. There's a pothole, or there's someone making noise at 4 in the morning, those kinds of calls. People take the calls, they record the data. It's all stuck in this database. And in this system, you can point at a place in the environment, and then we go out live to the database and get stuff along with data from other sources. So what does that look like? Basically, now we're building a digital twin of the city. So a little bit more ambitious than building a digital twin of a piece of equipment, for example. This is a very big piece of equipment, a lot more moving parts than your typical industrial thing would have. So here we're seeing a VR version of this. We're pointing at the ground. We're going out, in this case, getting georeference 311 records. You can see some tweets coming off from the side over there. You can look at one of these things, you can scroll through it and look at it. You can now see off on the right another person, because this is collaborative. They're doing similar kinds of things. And they can also work together with the person whose view that you're seeing over here. So to show you a little bit of this, what can we do beyond this, what we'll now do is to go into VR. And so this is shot, AR, this is shot through a video see-through display. This is a Vive Pro. A little bit more expensive than the regular Vive, but technologies that, because cameras, as we know, are incredibly inexpensive and keep getting better and better, courtesy of people wanting their phones to be better cameras. The idea of having things that have really high quality cameras built into them suddenly becomes a whole lot less expensive and pretty much close in price, getting closer and closer to the current non-camera equipped VR displays that we have. And so in this case, what I'll show you is a little bit of video. You're seeing here some other data we have besides the tweets. We have Yelp, for example, so you can look at a variety of things that are in Yelp. And off on the right-hand side, you can see just the lower left-hand edge of a bulletin board, which is shared with other people, in which you can clone copies of these little records. So together you can basically talk with each other, make hypotheses about how some of these records might be related to each other. And in this case now we'll look around and see some of those records. And you can see off in the center over there another person that you're working with. So we grab hold of this well-known Upper West Side restaurant's Yelp review. You can grab another one over there. Yes, there really is a place called Jacob's Pickles. We can move them around a little bit the way that you would with Post-it notes. We can grab hold of other things like some of those 311 reports that got up over there as well. So the point is that just with this very simple interface designed to be very walk-up and usable by people at a conference where we've shown this, you can already see how you can collaborate. And unlike back in the old days when you would have talked about this would be great for first responders and for people doing city planning who had the money to buy stuff, you know, this is all the same technology the kids use to go and play games, right? And in this case, all the data is completely open or, you know, within reason. You know, there's limits in what you can do with Yelp without having to pay the money, for example. But the point is that this is all accessible stuff. So this means you could not only have first responders and city planners using this, you could have someone making a decision about what am I going to do this weekend? Or, gee, I'd like to move to a new apartment. Let me, instead of having to physically travel around all of New York, let me go there virtually. Oh, cool, it's got some restaurants. That building has, you know, some apartments for rent. Maybe the apartment database is there. Those restaurants look good. Oh, the health rating doesn't look, oh, rats. There's another restaurant with rats. Maybe I don't want to live in that building, right? You know, so there's a lot of things that you can do interacting with this kind of data. So let me show you another application that we've been playing with. This is a collaborative motor rehabilitation. So the idea is to let a patient and a therapist who are not necessarily co-located be able to go and help that patient get better at what might be problems coordinating, let's say, the left and right hand sides of their body. Or even let two patients work together who are not physically co-located. So there is a lot of work that people have done with VR games for people working individually or people working remotely. A lot of them tend to rely on whatever they can get in terms of networking, which to the home tends not to have all that good a throughput and especially not very good latency. And so in this work, we're actually being funded by Verizon to work with 5G. We've done this work with pre-commercial and early commercial 5G, which has really good, really low latency. When we first got funded, they were suggesting that maybe we should do stuff with some of that remote maintenance assistance. But the problem for that is for many tasks, the SME shows you what to do. And if you see what the SME shows you to do, you know, a half second later, not a problem, that's fine, right? You'll just copy their thing. You see it a half second later, you probably won't even notice the difference, okay? We wanted something that was not gonna work with really good 4G, but only work with 5G. And so what you're seeing here is a domain in which each of two people, who are in this case communicating through networks on separate machines, is holding a pair of virtual handles, which we're using controllers for. The handles are connected to virtual elastic ropes. The virtual elastic ropes are connected to a virtual platform. The virtual platform has a virtual ball on it. And now the idea is, to start off really simply, we have two people. Can you keep the ball on the platform without having it roll off? Okay? So you obviously can move around a little bit to do that. If you are not well coordinated with your left and right hands, the ball is going to roll off, and that obviously is not what you want. If you practice a lot, you can actually make the ball bounce up and down on the board, and basically you can make this really, really hard. And I'll show you some video in a couple of seconds. The neat thing for this is if you ran this at 4G latency, where, for example, two people are trying to bounce the ball up, one says 3, 2, 1, bounce. 40 milliseconds later, after they've started and their end is up like this, you start putting your end up, then the board goes like this, the ball goes who knows where, okay? In this particular thing, experientially, 15 milliseconds is about the limit at which, when you play this, if you have those 15 milliseconds or more worth of delay, things don't work well, and you're not to blame, and you know your colleague is not to blame. It's the system. Get below that, it starts getting to the point at which you can actually do it comfortably. Working this with around 5, 6, 7, 8 milliseconds of delay, when the ball rolls off, either you blew it, or your colleague blew it, or you both blew it. Okay, you really feel like it wasn't the system, you just need to practice more. So this is what it looks like with two people that practiced a little bit. Now we're not just rolling it around, we're bouncing it around, right? And this is not easy to do and does not work well when the latency is, as I said, beyond single-digit number of milliseconds. Clearly better and better as the latency gets lower and lower, which you can actually do with 5G when we have good functional commercial deployments. So, one more thing I want to mention. So I've talked about a bunch of different approaches in which we have multiple people working together, whether they're co-located or whether they're remote. I want to talk about one thing in which the collaboration is with a single person, but with multiple different devices being used collaboratively. And so we build what I like to refer to as hybrid user interfaces, where we combine together different kinds of display devices, all working in the same 3D space. This is an older piece of work in which we were using a Microsoft first generation Surface, which Daniel knows really well, right? This is a rear projected, a really cool multi-touch tabletop device. We're using it here along with the Big Map API to show the footprints of buildings, and the nice folks at Microsoft gave us the actual building models. This is part of downtown New York. We put the buildings over their footprints, and of course that means you can translate and rotate and scale, because if you have a multi-touch display, you're obligated to do demos in which you always translate and rotate and scale. But when that happens, the 3D models translate and rotate and scale as well. You can look around, they protrude, they violate the bezel of the screen, obviously, which you get to see. And the cool thing is that if you are not wearing the head-worn display, you can still see the footprints, and so you can still be part of the conversation. And in fact, what we do is, because wearing the head-worn display, you can't see the footprint, it's covered by the building, we put data in the footprint that can now be useful to help bring up to speed the person who is not wearing the head-worn display, so they can see like a little rendering of what the building looks like, and other data that you would be able to see when you're actually looking at it. And again, you can have multiple people in the room, they can be interacting with each other, and then when a person walks in who isn't wearing the head-worn display for whatever reason, they don't feel like what's going on here, they can actually see, they can walk up to it. And then the other cool thing, of course, is that technologies like this are much more sensitive in terms of the touch sensitivity of that surface than any of the things that we have right now for hand tracking, for free hand tracking. So if I touch the surface a little bit, touch it a little harder, the Leap motion controller, let's say I have on my head, it can't tell the difference, okay? But that surface can, okay? So I really believe that even when we get the amazing head-worn displays that we're getting closer and closer to getting, we're going to still see lots and lots of wall-sized and floor-sized and ceiling-sized displays in the environment. They're not going to all go away. They're only going to get bigger and better than they are right now, and we're going to use them all together. So let me show you one more thing. This is a somewhat more recent version of a hybrid user interface. This is work that Pierre Amelot and other visiting me in my lab, my colleagues in my lab, did with other folks in the department back in 2016. This is using what is the name of Jeff's display that was the forerunner of the Surface Hub? It was before, no, it was another name. A perceptive pixel, yeah. So this is a perceptive pixel display before that technology got turned into Surface Hub. We're using it horizontally, again, a really nice touch-sensitive display. And we're basically going to be using this for a music exploration demo, in which we're using a combination of HoloLens as an AR head-worn display, the perceptive pixel multi-touch display, a Leap motion controller to do bimanual gesture input. They're all working together in the same coordinate system. And you might want to lower the volume a little bit because it's going to be a little bit loud towards the end. So we have a bunch of artists. We selected artists, and now we have this little shaft of light coming up courtesy of HoloLens. You can deselect Michael Jackson there. We have Daft Punk over here, and we're seeing albums within that shaft. Now we're doing some Leap motion controller gestures. Looking around inside there, we can then at some point decide we want to grab one of those. We grab hold of it, pull it out, turn it around a little bit. It's got a song list on the back. You know, we go back to doing more HoloLens things. We gaze at something, we get to go and have our voice interpreted. The system goes out to Spotify actually and plays samples from the songs over there. Okay, so I'm going to stop that at this point over here. I think I've reached the end of my talk. I've talked about a variety of different kinds of things we can do collaboratively in AR and VR in several different domains. And one thing I want to mention before I stop is that most of the things that I showed you, all of the multi-person collaborative ones I showed you, are all being implemented with something we call the Mercury messaging framework. This was a Kai paper last year at Kai. It basically provides a way for Unity programmers and the implementation that we have of it, of being able to have arbitrary parts of the scene graph talk with each other using a messaging protocol, so you don't have to write a lot of like low-level custom code. You use our messages, you can create your own messages, they get sent back and forth in a very efficient way, and it's going to happen within a machine and also across machines, so that you can have things that basically are distributed across multiple machines without having to worry about doing all the interesting networking yourself. And this is all done under BSD license, so it's all open source out there at the URL that I've mentioned. We encourage you to download this if you do stuff with Unity and do cool stuff with it. And so at this point, I basically want to acknowledge my colleagues and funding agencies that have funded this work. I've got the URL for Mercury up at the upper right-hand corner over there, and hopefully I have a little chance to go and have you ask questions and have me try to answer them. Thank you.
Thank you so much for that talk. We have about 5 minutes for questions, so I've got a couple microphones, so just put your hand up and I'll pass them around.
Thank you so much for the talk.
You're welcome.
It was really great, and it showed a lot of the amazing things that AR and VR sort of enable. But something that came up in kind of the last example is that the low-level input tasks in like a 3D context or a VR context are still not as good as they would be in, say, 2D.
Yes.
And like just target selections in 3D is harder. Typing
Yes.
with current headsets is harder. And like switching between a headset and like a desktop computer is hard because, as you mentioned, like just getting it on and off is a substantial burden. So this seems like a really important challenge that VR is going to have to deal with if it's going to move beyond like small, like independent applications and be part of larger workflows.
Absolutely.
So I was wondering what you thought like the solution to that would be.
A lot of it is technology, both hardware and software. There clearly are a number of folks working actively and trying to make much better bare hand tracking. There's been a number of neat things that have been done by a variety of companies that have gotten bought by a variety of other larger companies. And some of those larger companies internally are also working and trying to make stuff like that happen. And combinations of better sensors, interesting algorithms, including, obviously, you have to say those two letters, ML, right? And the fact that we're dealing with hands that only, and there's a certain number of things you can do with hands and other things you can't. They don't really pass through each other, though they can do stuff like this, right? And any of us looking at someone doing things with their hands can pretty much, maybe you can't copy somebody else, especially if they're really athletic, right? But you can kind of, at the still image, be able to see what they're doing, right? So there's no reason to think that we shouldn't be able to do that with good enough sensors and good enough algorithms. And as I said, there's a lot of people working on making stuff like that happen for everything from work to obviously a lot of things that are entertainment and play oriented. So I think we're going to see that. Head-worn displays, I really deeply believe in optical see-through AR in form factors that are much more like eyeglasses, ultimately maybe contact lenses, although I'm never going to wear contact lenses. I don't want to put things in my eyes. Ultimately, beyond that, direct hookups of the sort that are the subject of science fiction stories. Beyond that, genetic modification that will make the people with the direct hookups get mad at their kids for suggesting that they do it. So technology will march on. We will get better and better at doing stuff like that. And the cool thing is that at least with the current technology, which, in terms of displays and interaction, is far better than things we've had in the past for orders of magnitude more money, more and more people can actually step up to the bar, so to speak, and actually try to do things that will produce, advances over what people have done so far.
It was obviously you covered quite a few different systems, both in terms of recording motion and manipulation of different kinds of objects. I have one question, and I'm wondering if this is an area that you did any research in. So obviously, when it comes to say shape recognition, just the most basic context, stereo vision obviously helps. But
yes.
I'm also thinking of, say, something like surgery or a watchmaker or something. There's often the surgical lamp throughout, for example, a surgery is being moved around to get the right rendering of subtle details, and also supplemented often with a head-mounted camera. Say some mechanical activities also involve that. Did you do any research in terms of like passive lighting, or different lighting scenarios? And then to refer to your display, some of the examples were what we call, I guess, diffuse kind of rendering of shapes. And then there was the one example where you had the yellow and red barriers.
Yes.
That had a different type of rendering.
Right.
Did you describe that, or was that like a real-time?
Okay, that was done real time. One interesting thing is that obviously we all want to be able to go and render things to look as much like the real world as possible. It's a wonderfully easily described goal. The problem is if you really made certain things look exactly like the real world. I was trying to show you where something was supposed to go, and I showed you this beautiful rendering where the destination was exactly, it looked like it was really there. Then I would have to do something to show you, especially if there were multiple other ones that really were there, which one is the one that you need to go and put in place. And so there is, even before there were computers, when people made really good maintenance and repair manuals, they would use not only photographs and line drawings, but when they had a photograph and pre-computer, they didn't have Photoshop, they had airbrushing. And people would airbrush out like the candy wrapper on the floor, and they would highlight and do all sorts of things to make the photograph better, right? The photograph looked as good as a high-quality analog film camera could take back then, but that wasn't good enough to try to explain stuff. So you would have airbrush stuff, you would have arrows being added, what I like to refer to as meta objects. And so those lines, for example, the fact that they really stood out that way, they didn't look like a real piece of red or yellow string in the environment, that was a feature. If it looked too real, maybe it wouldn't stand out as much, okay, as we were trying to make it. And so the idea of having some of those things be rendered in a style other than what they would be rendered in if you were trying to show off how good you were at photorealistic rendering, I think makes a lot of sense in instructional environments like that. But at least at that level, we have experimented with that. But there's more sophisticated things that you can do with lighting that really have not been things that we have looked at in my lab.
Great. Unfortunately, that's all the time we have for questions, but let's thank Steve one more time for the fantastic. Thank you.